Alright guys, this is day two of continuity. So we're going to turn it to the back. And then without looking on the front, without cheating, because you just saw it yesterday and you just did the homework for it yesterday, I hope. What are the 3 steps for testing continuity? So we had them yesterday. So what are the 3 steps? Try to write them out yourself. Alright, here you go. So the first step is you see if f of c exists. So see if the y value exists, okay? And then the second step, find the limit as x approaches c of f of x and see if that exists. So you're finding the limit. The third step is to compare them. Are they equal? So find the y value, find the limit, are they equal? That's how you test for continuity, okay? So that next question, example 1 actually, is going to be a more straightforward version of like example 3 from yesterday, okay? So given this function, a removable discontinuity occurs. I know it's weird, but add that in for me, please. Discontinuity occurs at x equals -7. Even if they didn't tell you that, you should be able to figure that out. I'll remind you how. You're going to redefine the function to remove the discontinuity. Basically, you're writing a piecewise function, okay? And how would we start this piecewise function? Let's see. So if you have x squared minus 49 over x plus 7, that factors into x plus 7, x minus 7, so difference of squares. And then cross cross, what does that really mean? We crossed out a whole. So our whole is at x equals -7, right? So at x equals -7, we have a whole. This function now reduces to x minus 7, because if we divide that away, we get x minus 7. Okay, our whole is at x equals -7, but that's not a whole. A whole is a point, right? So you have a -7. How do you find this? Well, this is a new function. You plug that into that. What do you get? You get -14. So there is a whole at point -7, -14. And then we redefine the function. So we're writing a piecewise function. We're saying this is true. We can use this as long as there's a discontinuity at x equals -7. So as long as we're not at -7. So this is good everywhere except for where the denominator equals 0, right? So where x does not equal -7. Okay, what about when x equals -7? Because we want to remove the discontinuity. We want to fill in the hole, basically. So there is a hole here. To fill it in, we need to say at this reduced part of the function, we would have, at -7, we would have this reduced version. And then if we plug -7 into here, that's where we get the -14, okay? So there is our redefined function. Okay, so then the next question says, determine analytically if that is continuous at x equals 1. Okay, we have to do step 1. We have to find the y value. So which one do we plug it into? We plug it into the one that says equals. So you plug the 1 into here. You get 1 squared equals 1. Okay, that exists. We're good. Number 2, you have to find the limit. So the limit as we approach 1, we have to actually check both sides, but we already did this side, it was 1, so now we can do the left side limit. So we plug it in, we also get 1. That means the limit is just 1, okay? Okay, and then non-lazy, so since f of 1 equals, don't say 1 equals 1, don't be crazy. Since f of 1 equals, and then the limit, blah, 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 blah. So we can write it this way with an f of x, okay? We want to write f of x. So since f of 1 equals the limit of f of x, then f of x is continuous at x equals 1. This is as lazy as you can get, remember? You have to write therefore or comma, f of x is continuous at x equals 1. You need all of those things. Don't say continuous. Don't say f of x is continuous. Like tell me where it's continuous, okay? With this statement as well. All right, one more. This is different, sorry. Find the constant a, such that the function is continuous. Oh, so we want this to be continuous. All right, so for it to be continuous, let's see, there's a left side, there's a right side. Pretty sure I want the right side and the left side to be equal, right? So the left limit, if I plug in 1, is 3. The right limit, if I plug in 1, I want it to be 3, so I set it equal to 3, and then I solve for A. There you go. So plug in 1, solve. That's it. Okay? Okay, so the next part, find the discontinuity, if any. You don't have to graph these to know whether they're continuous or not continuous, okay? You know what this looks like. This is a parabola that goes up, and it's like, here's the xy axis, and it goes up and it crosses at y equals -9. But it's okay, it's continuous, we can tell. So we can just say none. So I draw myself a little picture to remind myself, no discontinuity. Okay, what about this? We know there's vertical asymptotes at x equals plus or minus 3, right? So what kind is that? So there's vertical asymptotes. I state it. I want to know everything, guys, on the quiz. I'm going to ask you all this information. And there's, what are those called? They're infinite discontinuities at x equals plus or minus 3. Okay, because those are, don't say plus or minus 3. X equals plus or minus 3. Okay, because those are lines. Those are two lines, which are the vertical asymptotes. Okay, the next one, I already started like factoring a little bit on the bottom. So what about this? What I care about is the denominator, because I'm thinking, okay, well, that's going to be vertical asymptotes. But then I realize I can cross out the x's. Ooh, if I can cross out the x's, that means that there is a hole at x equals 0. And then this is a vertical asymptote. So there are two things going on. Okay, I'll just show the whole thing. So there are two things going on. There is a hole, which we call a removable discontinuity at x equals 0. Actually, I'm going to fix this at 0, comma, and then if I plug in 0 into here, so this is my reduced 1 over, and if I plug in 0 into here, I get -1. So 0, comma, -1, I have a hole. Tell me that, okay? Tell me the hole. And then I have an infinite discontinuity where my vertical asymptote is at x equals 1, okay? This one right here, okay, let's see. So I have to see if anything weird happens at 1. So I find my left limit, it's 1. I find my right limit, it's 1. It's continuous, nothing weird happens. There's even an equal sign, we're good. So the left side is a line and the right side is a parabola, but it meets at the same place. So it might look something like a line, and then it meets the parabola, and then here's your parabola, here's your line. So it looks like that, okay? So that is, excuse me, that is continuous, okay. E and F, let's see. So for E, I care about what happens at that too. So again, I'm finding the left and right. So you do it first, don't always just copy me, okay? You do it first, and then we see something like that. So the left and the right, oh, they're different. The limits are different. So what does that look like if I wanted to draw it for you? I would have a left going to 2. So that's a line. So let's say the left goes to 2. There is a point there. And then at 1, sorry, and then on the right side, I have a negative slope, and then it goes to 1. So it looks something like that. If I was going to graph this, at 2, x equals 2, it would look something like this. And you can see from the graph, that's a jump discontinuity. Okay, so I'm just trying to show you what it really looks like and why that's the answer. Okay, okay, so cosecant. Cosecant is different. So remember, for cosecant, cosecant is 1 over sine, right? Okay, so we're going to think about this. So we don't want the bottom to equal 0. Because that's what we care about here, right? We're looking at the bottom, setting those to 0, seeing if there's like holes or vertical asymptotes. So we don't want that to equal 0. Okay, so when does this equal 0? When 2x, so 2x basically, this can't be 0 because when sine is 0, we have 0. So sine of 0 degrees is 0. Sine of 0 radians is 0. So when we have this, we're no good. We don't want that. And then we also don't want this. So remember, on a unit circle, where is the y value 0? On a unit circle, the y value is 0, the sign is 0 here, right? The y value is 0. And here, you always have to remember what the unit circle looks like, because this is 1, 0. This is negative 1, 0. This is 0. This is pi, right? 0 radians, pi over 2, pi. So we don't want this and we don't want this. Otherwise, that bottom part's equal 0. Okay, so I go ahead and solve. I divide by 2. I divide by 2. Okay, we have infinite discontinuities at x equals, and then I wrote this k because remember for cosecant, it keeps going. It like looks something like, I know it's been a long time, but cosecant looks like this, and then it looks like this, oops, and then it looks like this, and it just like keeps going, right? There's like lots of vertical asymptotes. So we see, oh, it's at every pi over 2. So k pi over 2, where k is an integer. Okay? Okay, and then the last two. So what does this mean? This is a step function. Any step function, there is going to be, like if you look at any step function, there's steps. So there's going to be jump discontinuities, right? So we can say there's jump discontinuities at every, you can say at every integer. It's fine, you don't have to use this. This is a way to write integer, okay? So jump discontinuities at every integer. All right, this one is interesting. This one says, okay, what about f of g of x given f of x and g of x? So we're going to plug in because we know how to plug in. So f of g of x, I plug that in to here. So instead of 1 over x, it's 1 over, and then x squared plus 5. And then here's my minus 6. Okay, so this is my function. So I want to know where the discontinuities are. So look at the bottom. Go ahead and try to factor. Oh, okay. Actually, it's plus or minus 1. There you go. All right. So give it a try, and we'll talk tomorrow.